Welcome back, Physics 30. So this is the next video in the series here. Now, what I like to do, I forgot to mention it, but I like to call this Type 1 projectiles. So Type 1 projectiles involves something being launched horizontally, and of course, analyzing part of it as if it were a horizontal movement, or sorry, just simply dropped. Now, if we turn to the next page, this here is going to be called Type 2. In which we're launching something at an angle like that. All right? But before we do that, what I'd like to do is take a look at the next page, this scenario here. We'll talk about this because it really is a horizontal case, right? So a boy on a small hill aims his water balloon slingshot horizontally straight at a second guy who's sitting up here. Okay? So he's here, distance of D away. At the instant the water balloon is released, the second boy lets go and falls from the tree because he thinks, oh my gosh, I can see this, I'm going to get hit, but if I let go, the ball will just go over my head. So that's his rationale. So that he made the wrong move. And of course, we know that he made the wrong move, assuming that this water gun can actually shoot this far, they will fall at the same rate. It's really like that motorcycle question, right? They'll fall at the same rate if they're starting at the same height. So we should likely mention that both the water balloon and the boy in the tree start falling at the same instant. And in time t, they each fall the same vertical distance since they both started at the same height. Okay, so what will happen is that they're at the same. The ball will and the boy will be at the same position. At the same position in time t. So as this ball goes its horizontal distance, they're both falling at the same rate. So if this is a very powerful gun, they may only fall slightly before it gets hit. Just like that. If it's kind of a less powerful, it may take a while to get there. But as long as this thing can actually, if this balloon is capable of hitting the tree here, if it's capable of hitting the tree, then it's going to hit the guy because they're going to fall at the same exact rate. All right, so with that, let's look at Type 2. So this time we have something being launched at an angle as opposed to horizontally. So a good example of this is a football being kicked. So the football is being kicked at 37 degrees with a velocity of 20. So that is an angled velocity like that. I'm just going to call it V. So angled velocity V. So we need to figure out the maximum height, the time of travel before it hits the ground, and how far away it hits the ground. Now really, to analyze this, what I'm going to have to do is think of it like, okay, so I have my V, and oh yes, look at this. It has a horizontal component and it has a vertical component. And this, of course, here is 37. And this is 20. So yes, Vx will have to do with any, oh yes, and remember, it's going to be constant throughout. It doesn't change. The horizontal V is the same throughout. So that's going to help me figure out, let's see, oh, here we go. We're going to use Vx for this. Vx So I'll use Vx, and then I'll be able to figure out how far it lands. I'll be able to figure out how far it lands. But I have to figure out Vx first, and I also have to figure out the time of flight. And then anything involving a height or time of travel, that's going to use the vertical part of the motion, the vertical component, Vy. So Vx, used for horizontal movement. Vy is used for anything vertical, and what's considered vertical is time of flight, height of rise, etc. All right, so but first, before we do anything, we're going to have to convert this 20 into a vertical and a horizontal movement. So let's do that. So Vx, of course, is the adjacent side. So the adjacent is, of course, cos. So Vx over the hypotenuse, and the hypotenuse in this case is that 20. So Vx is equal to 20 multiplied by the cos of 37. So that gives me a horizontal movement of 16.0 meters per second. And for a direction, I'll just say right, going to the right of the page. Looking at Vy, Vy is the opposite side of the angle. So that, of course, is sine. So Vy over my height. So 20 multiplied by the sine of 37, and Vy is going to be equal to 12.0 meters per second up. So that makes sense. If this is 37, this component is 16, this component is 12, and they all come up with making the hypotenuse 20. All right, so now that I have that, I can figure out the maximum height. So here's the interesting thing. If I throw something that has an angled velocity of 20, when the angle is 37, I'll have the same height as if I had thrown it straight up in the air, like I just don't care, with the Vy of 12. So that is the key thing to note there. So maybe I should make a note of that here. So launching an object with V equals 20 meters per second at, what was that, 37 degrees? Degrees to the horizontal has the same, I guess I should show you that, has the same maximum height, max height, and time up as an object launched straight up at 12.0 meters per second. So that's a key thing to note here with projectiles. So launching at 20 at this angle is the same thing as throwing it straight up with a Vy of 12. It'll have the same maximum height and the same time of travel upwards. So to figure out the max height, let's see here. So it's just like what we did back in 1.5. Vi is going to be equal to Vy. So Vi is equal to Vy. Vf at the very top of the path, of course, is 0. I'm looking for D. I know what A is. So yes, we have this relationship from before. So at the very top of the path, we're not moving. Vi is if I had launched it straight up in the air, 12. And then, of course, here I have 2 times negative 9.8 multiplied by the D. So over here, 12 squared is 144. 2 times negative 9.8 is negative 19.6. So, of course, if I want to get D by itself, yeah, I'm going to have to get rid of this 144 first. So subtract, and I get negative 144 is equal to negative 19.6 times delta D. And you see I'm going to get rid of these negatives, which is good because the D needs to be a positive because we're going straight up. And maybe let's move over to here where I have more room. So negative 144 divided by negative 19.6. The D will give me 7.35 meters per second. Or sorry, just meters. Straight up. I'll just call it up for direction. Okay. And the time of rise. Let's see. Time of travel before it hits the ground. So just like before, let's figure out T up first of all. So it's like this. VI equals VY, which is equal to 12. And of course, VF at the very top is going to be 0. So VF is equal to VI plus A delta T. So at the very top of the path, 0. Launched vertically, 12. And of course I have negative 9.8, 0 multiplied by T. Subtract 12, subtract 12. Negative 12 is equal to negative 9.8 multiplied by T. And then the solve by T for T, divided by negative 9.8, divided by negative 9.8. And delta T is going to be equal to 1.22 seconds. Now, so that is time up, the time to go up. Therefore, total time is going to be 1.2 seconds multiplied by 2, 2.44 seconds is the time of flight. Because it's symmetrical. Symmetrical path. And as we see, type 3 is going to be a non-symmetrical path, and there's a few things we'll have to do with that. So we know the time up, 1.22 seconds. So whether I throw it up in the air or launch it at an angle, 1.222, 1.222. I guess just 1.22. And then lastly here, C. How far to the right does this thing go? So, of course, horizontally I have, yes, constant velocity, right? So, horizontally, 60 meters per second, continuously to the right. Uninterrupted, assuming air resistance is negligible. dx over my time of flight, 2.44. I don't know about you, but I just have this little corner to work here, so hopefully I can get it done. So I'm going to have 16 multiplied by 2.44. So that's going to give me 39.0 meters, and I'll just simply call that to the right. So that is the range in which my projectile will go for this particular question. All right. So with that, I think you should be able to do questions 4 and 5 from the assignment. And then that'll leave the last question 5 to be of the type 3, one that we'll do in the next video. All right, we'll see you again.